Hi, today we're going to talk about deriving three-dimension heat diffusion equation for a Cartesian coordinate with volumetric heat generation. So what we're going to do first is we're going to imagine, just move my computer. So we're going to imagine a, a 3D cube. And in this cube, we're going to have heat flowing in and heat flowing out. Heat flowing in and heat flowing out. So Q out and then Q in. But in this question, when we're talking about heat storage, we take into account all three coordinates X, Y, Z. So I'm just gonna draw it out so it's easier for you guys to imagine it. So it's gonna be change in the X direction. No, change in the X direction, change in the Y direction, and then change in the Z direction. So it's gonna be like this over here. So this gonna be dy, and this side is gonna be dx, and the up above is gonna be dz. So first, I'm gonna write out the energy balance equation. Energy balance equation. So to find the heat storage, I'm just gonna write ESD. Heat storage is equal to heat generation plus total heat flux. So first, energy storage is, we know that the unit of energy is joule. So how do we relate all of the variables that we have learned to find joules? So first, we can have density times heat capacity times the gradient of temperature, the over time. So energy storage is similar to accumulation. So that's why we have this. And then we times it by the distance or the volume. So the volume of this cube is going to be dx times dy times dz. dy times dz. So this is going to be the volume. I'm going to do a little one dimensional analysis just to show you guys why do we relate these variables? Because density give us volume over mass, meter cube over actually, I'm sorry, it's the other way around. That's specific volume. So it's going to be mass over volume, kilograms over meters cube, times heat capacity is joule over kilogram times K. And then the the temperature gradient is going to be K or C over time. And then volume is going to be meter square. So we cross out. We can have um joules over seconds or watts, which is the desired unit that we want because it has this little dot which represents the flow of energy storage over time. So that's we just first derived the energy storage equation, and then let's move on to the second one, the energy generated. This one is also pretty easy. Um, we also want the unit to be the same as the heat energy storage. So we're gonna have the heat flow times the volume again. So heat flows times dx, dy, and dz is the heat that was generated. And heat flow has the unit of volumetric heat flow. I'm sorry, I made a mistake. So it's actually volumetric heat flow. So it's going to be joules over second over meter square, meters cube times meter cube. So we have joules over. Don't forget about we're still talking about time here. And then and then this third one would be the total heat flux. So this heat flux would mean heat flux on the enter the surface in and out. And since we're working on a three-dimension model, heat flux come from all three directions, X, Y, and Z. But we're just gonna work on X for now. And so first we would have the X temperature in X. We would have the curve. in that the curve F, and we want to, let's say, measure the change in temperature of between 2 points x naught and x. So let's say we have x naught over here and then x. So what do we do? How do we approximate? Because we can't use a linear interpolation because this is not a linear curve. It's not a linear line, it's a curve. So we're gonna do something called Taylor approximation. So let's just imagine um over here and over here. We can, so basically what Taylor approximation is similar to linear interpolation in the mathematically. So we approximate the point using the slope of temperature and treat it like a linear. So we see that we can find the slope because we see that the slope is pretty similar like linearly. So in this case, the slope would be dt over dx, where x is x naught. The x begin with x naught. So we would have over here q x plus dx is equal to qx. So like the heat flows over here and the heat flows over here. We're desiring to determine the total heat flux. So we would need to find heat qx and qx plus dx. So we using Taylor's approximation, qx plus dx is I wouldn't write the equal sign. I would just say approximately equal to qx plus the temperature gradients dt over dx, where x equals 0 times the distance. So like x minus x naught, or just dx, delta x or dx. But we're gonna go with dx, okay? So now we need to find the heat flux, and we know that, let's go back to this. Heat enters through the x coordinate this way. X coordinate in this direction. Use a different color. So go through qx, qx, I'm just gonna write, this is an example, okay? X plus dx, and then qx. So to find the heat flux, we need to, so qx flux is equal to, goes out is negative. So we would have qx minus qx plus dx. And this is equal to, because we already derived this, the value of qx plus dx. So it's going to be qx plus dt dx, x equal to x naught times dx. And then these cancel out. So our heat flux is only negative. Oh, I'm sorry, guys. I made a mistake. So over here, this should have been dq x instead of dt because we're talking about the change in the heat flow, not temperature. So this one is gonna be q x, not t. Sorry, I made a mistake. So we would have over here, it would be qx, so dqx over dx times the distance is what we have for flux. So now when we plug into our equation, our energy balance equation, we would have density times heat capacity times the change of temperature with respect to time equal to the energy generation times dx, dy, dz as the volume plus or minus, because we know that this is a minus sign. So minus derivative dqx over dx time delta x or dx as the distance. Be careful right here. So this d and this are different. This d represent the distance, so the difference in the position of x versus x naught, for example. And then this is how heat change with respect to the distance. So it's, I just want to let you guys know to avoid any confusion. So now we can plug in Fourier's law to solve this. So we would have density times heat capacity with respect to temperature, respect to times equal to, I'm sorry, I forgot. We're missing dx, dy, and dz just for the volume. So dx, dy, dz is equal to q, dx, dy, dz minus, just gonna put the dx, ddx over in the bracket, and then we would have negative k, a, dt, dx, and then dx at distance at the end. So I'm gonna draw again so I can show you guys what the area represents, okay? So we know that heat goes over X, and in Fourier's law, the area is the cross-sectional area that heat cross. So that would be this area. Oops, this area. And this area is made up of dx, dy, and dz. So dy and dz created this area that the qx, that heat flows in the x direction. So we're gonna plug a with dz and dy. So we're gonna have, it's gonna copy this equation again down here. And then we would have a is dy, dz, and then dt, dx, and then dx. So now we see that we can cancel out the volume. So we're gonna do that. Oops. Sorry about that. We're gonna cross out the volume. Now we have a new equation. Also, we can just, yeah, we can just do this. T dx squared times k times q. And then we can move density and heat capacity over to the right side. So we have dt, change in temperature over time, over kpc plus q over pc. So we know that this is the thermal diffusivity constant alpha. And so now what we're gonna do next is we know that we always work a lot of our questions, we assume steady state, so we're gonna do the same. So in steady state, temperature stay the same through time. It only changes with respect to direction, but with time it's the same for everywhere. So in steady state, dt over the temperature over dt is equal to 0. So we have 0 k dc times this plus u. And we can just move cancel out density and heat capacity. We would have k dt change in temperature, the second derivative change in temperature with respect to distance plus q. So now we're gonna move q over to the other side. We're gonna have negative q and we do the same for k too. And now we can so now we see that the second derivative of temperature is a constant. So we know that temperature has a parabola shape. So now we can find an equation that represents temperature. So I'm gonna rewrite this equation over here. This is a very easy step. We can just do simple integration. Over here, oops, sorry, that was for the next part. I'm gonna move this. I'm gonna add another page here. Page. Yes. And so let's say the integration of this is equal to dt change in temperature with respect to distance is q over k x plus c1. And then we do another integration. We would have t is equal to negative q over kx squared, 2kx squared plus c1x plus c2. And then now we're gonna draw just a demonstration of the temperature profile would look like. let's call this x equal to 0 and then x equal to L. Just like x can be anything. We can call x give any value, any variable, it doesn't matter. And then this is T at L and this is T naught at 0. And then so the velocity temperature profile would look something like this, where it has parabolic shape. And so let's say at T equal to 0, x is equal to 0, so we cancel out this and this, right? So we would have C2, and then T at L, temperature at length L, would be equal to negative Q over 2K times L squared plus C1 L plus C2. And so now that we know the value of T0 and TL, we can plug it into our equation. So we're gonna use this equation. dt equal to dx equal to negative Q kx plus C1. So we're gonna have T L minus T0 over L. So the difference in temperature with respect to difference in distance would be equal to negative this would be equal to negative QK L squared plus C1 L plus C2 minus C2, because we determined that T naught is equal to C2 over length. And then we cancel out. So we would have Q over 2K L plus C1 equal to T L minus T naught over L. So yeah, C1 is equal to TL minus T naught over L minus Q over 2KL. So that's how we derive an heat diffusion equation for a Cartesian coordinate with volumetric heat generation. And so yeah, and so now we're gonna move on to the next question for one dimension heat diffusion with heat generation where inside is insulated, and derive an expression for temperature profile and sketch. Explain why the temperature gradients increases always insulated inside. So first we're gonna draw the scenario out, okay? And then actually, and then there would be the right size insulated. So we're gonna have let's call this x equal to 0, and then over this size x equal to L. And so we can have this one starts exposed to open air. So we're gonna have heat transfer by conduction. So heat flows again goes from higher temperature to lower temperature into this direction of heat flow. And then we assume that it's in steady state as well. So you know that steady state is change in temperature with respect to time is equal to 0. So there's no accumulation. And so heat flow going the other way, and we set up our coordinates x, y, positive direction. So since heat is going away from the positive x direction, we would have heat is negative. Okay, so now we're gonna use apply Fourier's law. We have negative k is equal to negative dt negative q. I'm sorry, equal to negative ka dt dx. But now we're doing since we're taking account of 3D dimension, we can have to take account in all three directions, x, y, and z individually. Okay. So when we talk about heat storage or heat flow in a 3D model, we have to take volume into account. So we can have to times the heat flux. So heat flux times volume. So we would be able to find the amount of heat stored per volumetric. Okay, so we can have negative Q A times L equal to negative K A dt dx. Now we cancel out all of A, we would have, and then cancel out the negative sign, we would have, let me move myself. We would have, dt over dx is equal to Q over K, QL over K. So now Q is the heat flux, or net heat flux, net heat flux of each of the direction individually. So X, Y, and Z. And then L is just the distance. So for example, like for instance, dx, dy, dz. So now we're gonna find the heat flux for each of these individually. And then we're gonna apply it into our energy balance. So overall, this entire thing is just not generated, the heat flow, the net heat flux that we learned in the first chapter. So now let's do this let's find the heat flux for each of the coordinate. Okay, so for x, we know that qx minus q dx, qx minus qx plus dx is equal to q minus qx plus derivative of dqx over dx times the distance, so dx. So we will just have this. And then for y, it's the same thing. So qy minus qy plus dy is equal to qy minus dqy over dy times dy, distance of y. And then same for z, qz minus qz plus dz is equal to qz, qz minus qz minus dqz over dz times dz. So now we cross out all of this. We would just have these variables left for our equation. So now we can apply it. Okay, we would have the heat storage density times heat capacity times the change in temperature with respect to time equal to heat generations. Oh, and then the volume too. I always forget this over here. Equal to Q energy generated, and then we would have let's see what's over here. So d, we would put d over dx on outside. So d over dx is negative k a, because we're substituting q just like before by substituting Fourier's law. Substitute Fourier's law. Ka d t over dx times distance of x plus, do the same for y and z as well. So negative ka dt dx times the distance, because distance over here, so times the distance times dz negative ka dt over dz times dz. And then, so now what we see over here is we can substitute a just like we did for the other question. So a for x, the area, the distance that would make up the area is dz and dy. So dz and dy, and then for y, it would be dz and dx. And then for z, it will be dx and dy. So now we're able to cancel out all of these terms for areas. And then let's rewrite this. Pc dt is equal to q plus d dx. Yeah, let's just, let's see. K negative k sub k minus k um dt squared dx second derivative of x, y, and z with respect to x, y, and z, I mean. Then we move density and heat capacity to the right side. We would have this too. The alpha is heat diffusion constant. And then repeat this. And then we know that it's steady state, this will be 0. So we have this, and then we're just gonna uh and then we know that we treat heat as Q is equal to 0, as in there's no heat generated. So we would have, this is our final equation. And then now I'm gonna draw the temperature profile for this case. Then so this is what the temperature profile looks like. And so the question is, why is the gradient greater when it comes closer to the surface compared to when it gets closer to the insulation? This is because there's no heat flows generated here. So there's no heat flow generated from this side. So when it goes towards the end, there would be more heat flows from all this area that was generated. That accumulates, the heat would accumulates from further away. So the greater the distance away from the insulated, there's more heat generated. So this is why the flux at the end, at the air would be greater than the flux at near the insulated side. So let's say, for example, if you divided this by half, then only this volume or this area of the object where heat is generated compared to the entire thing. So if you fold it in half, that would be less heat flux compared to if you have it longer, because it has to generate heat for all of the area before it. So this is why heat flow is higher, and which makes the temperature gradient increases as it gets further away from the insulated side. So for this question, we're gonna apply finite approximation to derive an expression for the relationship between each nodes by creating or simplifying A1 for a case of steady state, two-dimension heat diffusion with no heat generation. So we're gonna write down the energy balance equation to see what it looks like. Okay. So we're gonna have we're going to use the version that we derived earlier. So change in temperature over change in time is equal to alpha times change in temperature, second derivative with respect to x, y, and z. And z times heat generated. So now, since it's a two-dimension, we cross out z and there's no heat generation. We cross out these two variables too. So we would have dt a times dt squared over dx squared plus dt squared over dy squared. And then we're gonna draw the scenario, okay? Gonna have, let's say, a block, a 2D block, x and y. And then we're gonna divide it into small parts. And let's just choose this point where we have I and j. So I and j is the iteration of delta x and of x and y, and then we have n for time as well. And then so this is I equal, it's just I plus 1, I minus 1. So I plus 1 would be over here, over here, and then I minus 1, and then j minus 1, j plus 1. J over j plus 1, I over j minus 1, I minus 1 over j, I plus 1 j. So now we're going to write the equation, apply this concept into our equation. So we would have t n at this point. So t n plus 1 minus t n over delta t equal to alpha times ti j, ti plus 1 over j minus tij over delta x minus tij minus tij, ti minus 1j minus 1j over delta x. This whole thing over delta x as is the second derivative plus tij plus 1 minus ti. So this is for the y direction. J minus, oh, and then we minus this too, minus tij minus tij minus 1 over delta y over delta y. And then so we can make some a couple assumption here. So we assume that delta x is equal to delta y, and then its steady state means dt over d. Change in temperature with time is 0. So we cross out this, and this. So we only have this expression left, minus 4 tij plus ti plus 1j plus ti minus 1j plus tij plus 1 plus tij minus 1. And then we bring tij over to the other side, and we would just have the temperature of that specific location is the average of the temperature of its left and right, top and bottom. So all four direction of that location, the temperature of location would be the average of the temperature of four direction or four nodes that's adjacent to that. That's I and j. Be over 4. And then so this is the expression for the temperature at a specific node. So average of the neighboring nodes. So up, down, or top, bottom, left, and right. And then we can do an Excel for this too in the next part. Hi, so for this last exercise, we're gonna do we're gonna apply finite approximation into our Excel, okay? So in our questions, we have temperature on the left is constant at 100 temperature, and then the temperature on the right is constant at 200 temperature, and then temperature on at the bottom is constant at 250, and then temperature at the top is constant at 310. So first thing first, we're gonna do it like a simulation, like what we did with the block, where we divide it into a different portion. So we're gonna treat the cells and X cells like that. So the top, for the top, we would have 310 as the constant temperature of the top, and then at the on the left, we would have 100. Strike it to 20, and then at the bottom, we would have 250, and then on the right, we would have 200. And then we can apply the same formula that we did. The temperature at each node is related to the average of the temperature at its neighboring node. So this one's going to be equal to top node plus the left node plus the bottom node plus the right node, which is FA. And then divided by 4. We have like 102, and then we just drag down. And then we can drag it all over here. Let me redo this. So therefore we have this chart and each block should have the same formula or iteration. So for example, this one, it would be K13. So it for neighboring blocks should have been L13, J13, K12, and K14, which is what we have up here. So this is how you demonstrate the finite approximation on Excel. Thank you so much.